On the 13th of April, 2029, an asteroid the size of 3 football fields will pass closer to Earth than our own satellites, the closest approach of an object this large in recorded history. About 2 billion people will watch it cross the sky with the naked eye. It will not hit us. But the closer scientists look at this rock, the stranger it gets, and in 2029, Earth's gravity is going to squeeze it. By the end, you will understand why scientists are worried and what they are about to find out. On the 13th of April, 2029, an asteroid named Apophis is going to pass about 31,600 kilometers above the Atlantic Ocean. That is closer than the satellites you rely on every day. The ring of satellites that carries television, weather data, and a large share of global communications sits at roughly 35,700 kilometers. Apophis is going to come in underneath them. It will pass at about 1/10 of the distance to the Moon, and it is the closest predicted approach of an asteroid this size in recorded history. This object is not small. Apophis measures somewhere between 340 and 375 meters across, about the length of 3 football fields laid end to end. For one night, roughly 2 billion people across Europe, Africa, and Western Asia will be able to watch it cross the sky with nothing but their own eyes, a moving point of light brighter than the stars in the handle of the Big Dipper. No telescope required. An object the size of a skyscraper passing close enough that you can track it by eye. Here's the part I need you to hear clearly, right up front. Apophis is not going to hit Earth. That has been ruled out with confidence for at least the next 100 years, so this is not a doomsday story. But it has become something stranger and, in some ways, more interesting because the asteroid itself is not behaving the way a simple rock should. The closer scientists look, the more the numbers stop adding up, and in 2029, our own planet's gravity is going to reach out and stress this body in a way nothing has in millions of years. Nobody can tell you exactly what happens when it does. That uncertainty is why the people who study this thing are quietly on edge, and it is what we are going to break down right now. To understand why the object matters more than the orbit, you have to go back to when Apophis first scared everyone. The asteroid was first detected in 2004, and within months, the people calculating its path saw the impact probability for 2029 climb to about 2.7%. That does not sound like much, but for an object this large, it was alarming enough to set a record. On the scale astronomers use to rate asteroid threats, Apophis reached the highest level ever assigned to any asteroid, before or since. For a short window, this was the most dangerous rock we had ever found, and it already had a date attached to it. Then the science did its job. Astronomers kept tracking the asteroid, and in 2021, they used powerful radar to pin down its path with extraordinary precision. The result was a clean all clear. An Earth impact was ruled out for at least 100 years, and the small chances of a later strike, in 2036 and 2068, dropped to nearly nothing. We now know where Apophis will be in 2029 down to the kilometer, and that is exactly where the real story begins, because knowing the path is not the same as knowing the object. We have measured the orbit of this asteroid better than almost anything else of its kind. We have barely measured the asteroid. We know its address, and we do not know its character. For most of the time, Apophis has been in our catalogs. That gap did not matter because nothing was going to disturb it. In 2029, something will. So the question stopped being, where is it going, and became, what is it actually made of? And what happens when Earth grabs hold of it? The first clue that the answer is strange came from a single stubborn measurement. This asteroid weighs far too little for its size. Density is one of the most powerful numbers you can measure about an asteroid because it tells you what the thing is made of and how tightly it holds together. Apophis comes in at about 1.75 grams per cubic centimeter. Solid, stony rock, the kind you would find in a mountain on Earth, runs closer to 3. Apophis is barely more than half as dense as the rock it is supposedly made of, and there is only one good way to explain that. The asteroid cannot be a single solid boulder. It has to be full of empty space. The estimates put that empty space, the porosity, at around 40%. Almost half of Apophis, by volume, maybe nothing at all. That is the signature of what scientists call a rubble pile. The picture is not one mountain hurtling through space. It is a loose heap of gravel, boulders, sand, and dust, thousands of separate pieces held together not by any glue, but mostly by their own weak gravity. A rubble pile is closer to a floating pile of sand than to a stone, and it is held together by a grip so faint that a strong enough tug from outside could rearrange it. We are not guessing about this. We have visited objects exactly like it. When Japan's Hayabusa spacecraft went to a small asteroid called Itokawa, it found a rubble pile, a jumble of loose material with almost no solid core. Apophis closely matches Itokawa in the ways we can measure. When NASA's OSIRIS-REx mission touched the asteroid Bennu to grab a sample in 2020, the surface behaved like a pit of plastic balls, and the spacecraft sank in farther than expected before backing away. These objects are not the solid mountains our imaginations picture. They are flying rubble, and Apophis appears to be one of them. That alone would make the 2029 encounter worth watching. But the shape made it stranger. When radar imaged Apophis during its 2021 approach, it produced the first real look at the asteroid's shape. And the shape was not a simple potato. It was elongated, pinched in the middle, with two distinct lobes joined by a narrower neck. The scientists who described it kept reaching for the same words. It looks like a peanut. It looks like a dumbbell. It looks like two rocks stuck together. That shape has a name. We call it a contact binary. Two separate bodies that drifted together long ago, touched and stayed touching, held against each other by their own faint gravity. This is not rare. Roughly 15% of near-Earth asteroids larger than 200 meters show this two-lobed form. But common does not mean safe, because a shape like this comes with a built-in weakness, and that weakness is the neck. Think about anything you have ever held that was made of two pieces joined together. Where does it fail, if it fails? Not through the solid middle of either piece. It fails at the seam. The neck of Apophis is its seam, the narrowest, most fragile part of the entire structure, the place where the two halves meet. And a seam becomes dangerous the moment something starts pulling the two pieces in different directions. Hold that image, because in 2029, Earth's gravity is going to pull on this asteroid hardest at exactly that point. The shape is not just a curiosity. It is a map of where the asteroid is most likely to give, and the way Apophis moves through space points at the same conclusion. Most objects in space, left alone long enough, settle into a simple, steady spin around one axis, the way a planet turns on its pole. Apophis does not do that. Apophis tumbles. It rotates around more than one axis at once, so that it wobbles and rolls as it goes, never settling into a clean spin. The main rhythm of its tumble takes about 30.6 hours, and layered on top of that is a slower wobble that takes around 263 hours. Picture a football thrown by someone who has no idea what they are doing, end over end and sideways at the same time. That is how this asteroid moves. This matters because of what a tumble reveals. The way a body rotates is set by how its mass is arranged on the inside. A smooth, uniform solid tumbles one way. A lumpy, uneven body, with denser regions in one place and looser, emptier pockets in another, tumbles differently. So when an asteroid's spin does not match what you would predict for a uniform rock, that is not a mystery for the supernatural. It is a fingerprint. It is the interior leaving its signature in the motion. This is the detail that has lit up so much of the conversation online. A theory circulating right now points at the spin of Apophis and argues that it does not match a solid body, and concludes that something inside is shifting. The specific numbers being passed around are not ones I would trust, and you should treat them with caution. But the instinct underneath the claim is pointing at something real. An irregular tumble is exactly what you would expect from an uneven, loosely packed rubble pile. The spin is one of the only windows we have into the part of Apophis we cannot see, and it is telling us the inside is not simple, which raises the obvious question, what happens when you take a loosely held, lopsided pile of rubble and squeeze it with a planet? The force at the center of this story is one you already know. It is the same force that raises the ocean tides. Gravity gets weaker with distance, so when Earth pulls on an object as large as Apophis, the near side gets pulled harder than the far side. The whole body feels a stretch. On the ocean, that stretch lifts the tides. On a loosely bound asteroid passing 31,000 kilometers overhead, it becomes something far more interesting because the asteroid is also tumbling, so different parts of it swing into that line of maximum stress over and over during the hours of closest approach. Earth does not pull on Apophis once. It works the asteroid, like hands kneading a lump of dough. So what do scientists actually expect? Modeling groups that built virtual versions of Apophis out of thousands of particles agree on the headline. The asteroid's spin will change, and it will change enough to measure. Apophis will most likely stay a tumbler, but its spin rate could roughly halve, or it could roughly double, and the direction it points could shift. The physical deformation of the body, the actual squashing, is predicted to be small, on the order of centimeters, and mostly elastic, meaning it springs back. The most likely outcome is not destruction. It is a measurable change in spin, plus some small surface disturbances. Those disturbances are worth watching, and they concentrate at the neck. When the models look at where the stress piles up, the answer comes back the same way nearly every time: the waist between the two lobes. The encounter could relieve the compression that holds those lobes together, letting one shift slightly against the other. It could also trigger landslides. On a body held together this weakly, a small change in spin can set loose material sliding. And those slides could expose fresh, unweathered material that has been buried for ages. We could watch an asteroid partly resurface itself in a matter of hours. Now, there is a hard physical reason Apophis will not simply fall apart, and it is worth knowing. There is a line in space called the Roche limit, the distance inside which a body held together only by gravity would be torn apart by tides. For Earth and a body this light, that line sits around 18,000 kilometers from the planet's center. Apophis passes about 38,000 kilometers from the center, well outside it. It enters the zone where it gets stressed and disturbed, not the zone where it gets dismantled. That is the reassurance. But it does not end the suspense, because the real question is not whether it survives. It is how much it changes, and that depends entirely on the interior we cannot see. You may have seen the more dramatic version of this story online. The claim is that Earth's gravity could flex the fragile neck until Apophis breaks in two, and that one of the pieces could then slip through a gravitational keyhole, a narrow point in space that would set up a future impact the whole body would have missed. I want to be fair to it because the kernel is real. Necks are weak points. Contact binaries really can come apart under tidal stress. The instinct is not crazy, but the science does not support the leap. The detailed modeling predicts only centimeter scale, reversible flexing, not a break. Apophis passes outside the Roche limit, so gravity alone cannot pull it apart. And even in the extreme case where the neck did give, the two lobes would drift apart at a few centimeters per second at most, parting by meters over hours, nowhere near enough to thread a keyhole less than a kilometer wide that the combined body was already measured to miss. Stack those unlikely steps together and the probability collapses towards zero. The impact stays ruled out for a century. The viral version takes a real mechanism and turns the dial far past what the data allows. The honest story is the suspense over how much Apophis changes, not a fear that it shatters. Here is what actually has scientists on edge, and it is not any single prediction. It is the spread of the predictions. Every one of those models had to assume something about the interior, the one thing we have never measured. A stronger, more tightly bound interior gives you the gentle version, a small spin change and little else. A weaker, looser, more lopsided interior gives you the dramatic version, a large spin flip, real shifting at the neck, visible landslides, a face we have never seen. The models cannot tell us which one we will get. They can only tell us the range, and the asteroid alone decides. Apophis is going to answer a question we have been asking for 20 years, the question of what it is truly made of inside, and it is going to answer it by how it behaves when Earth squeezes it. A big, surprising change tells us the interior is weak and strange. A barely detectable one tells us it is stronger than it looks. Either way, the moment of the flyby is the moment the answer finally comes out. That is why this is not a calculation we can run in advance. We have to watch. Which makes the next question the most important one of all. When this happens, who is going to be watching and how closely? For nearly every close encounter in the history of the solar system, nobody was there to see it. In 2029, that changes because we are sending hardware to meet Apophis. The first spacecraft has one of the great second acts in space exploration. You may remember OSIRIS-REx, the NASA mission that flew to the asteroid Bennu, grabbed a sample and parachuted it into the Utah desert in 2023, the first American asteroid sample ever returned. That spacecraft is still healthy and still flying, so NASA gave it a new name and a new target. It is now called OSIRIS-APEX, and its entire job is to chase down Apophis. The way it arrives is precise enough to sound like science fiction. OSIRIS-APEX is timed to reach Apophis right around the close approach, passing about an hour behind the asteroid as the system sweeps past Earth, then using Earth's own gravity as a slingshot to catch up about a week later. From there, it settles in for roughly 18 months, mapping the surface, reading the chemistry, and watching how the asteroid turns. And it will do one thing that matters more than anything else for our story. It will descend to within about 5 meters of the surface and fire its thrusters downward, blasting away the top layer to expose the fresher material underneath. After 2 hours of me telling you the inside of Apophis is a sealed box, this is the spacecraft that flies down and blows the lid off a corner of it, on purpose. It will not be alone. The European Space Agency, working with Japan, is building a second mission called Ramses, and it has a different and equally important job. Ramses is designed to launch around 2028 and arrive at Apophis in February of 2029, about 2 months before the encounter. That timing is the whole point. Ramses gets there early, so it can measure the asteroid in its undisturbed state, the before, and then ride along to record the after. An experiment only means something if you measure the starting condition, and Ramses is the baseline. Between these two spacecraft, we will have a detailed before and after of an asteroid being reshaped by a planet, which has never been done. The most numerous instruments that night will not cost a thing to build. They are human eyes. While the spacecraft do the precise science, roughly 2 billion people across Europe, Africa, and Western Asia will be able to step outside and see Apophis move across the sky, brighter than the stars of the Big Dipper, over the course of a single night. For once in our long history with the objects that share the solar system, the public will witness the event directly, in the moment, instead of reading about it the next morning. And behind the crowds and the spacecraft, the professional observatories of Earth will be locked on. Powerful radar dishes will hammer Apophis with radio waves during the closest approach to read its shape and spin in detail, the same technique that first revealed its 2 lobes, now trained on it during the very hours it is being stressed. Telescopes will track its brightness for the subtle flickers that betray a changing spin or freshly exposed ground. Between the eyes, the spacecraft, and the radar, almost nothing about that evening will go unrecorded. These are the detectors wired up to the experiment, and the only reason the experiment is worth running is that this time we are finally in position to read the answer the asteroid gives. There is a practical reason that people who study this treat 2029 as a gift, and it reaches far beyond one rock. Somewhere out there is an asteroid that will not miss, on a year nobody has circled yet. If we ever have to push such an object off a collision course, the single most important thing to know is what it is made of inside, because you cannot move a rubble pile the way you move a solid rock. We have already taken the first step, and it proved the point. In 2022, NASA flew a spacecraft called DART straight into a small asteroid moonlet named Dimorphos on purpose and shifted its orbit. It was the first time humanity ever deliberately moved a celestial body. But the surprise was the lesson. Dimorphos turned out to be a loosely bound rubble pile, and when the spacecraft hit it, it splashed, throwing out a huge plume of debris that pushed the asteroid harder than the impact alone would have. The softness of the body changed everything about how it responded. Hit a solid rock, and it moves like a solid rock. Hit a loose pile, and it might absorb the blow, or splash, or break into pieces that keep coming. You cannot plan that maneuver without knowing the interior, and the interior is exactly what Apophis is about to reveal. The free lesson it hands us in 2029 is the same knowledge we would need to protect the planet from the next one. So here is where things stand. Apophis is the most studied dangerous asteroid in history, its orbit is locked down, and it is not going to hit us. But it is also, at its core, a sealed box, a loosely bound pile of rubble whose interior nobody has ever measured. And in 2029, our own planet is going to run the one experiment that can finally open it. The spin change, the behavior of the neck, the landslides, all of it will be measured by 2 spacecraft and watched by 2 billion people, and the asteroid's response will tell us what it truly is. The one honest piece of uncertainty that remains is not a hidden danger. It is simply that the interior is unmeasured, and that there is a small chance an undetected object could nudge the asteroid's path slightly before 2029. That is the frontier of what we know, not a cover-up. Everything about this asteroid has been published in the open, which is exactly why we can tell you the orbit is safe and the object is still a question. We will be tracking this closely as the date approaches, because the missions launch in the next few years and every new observation sharpens the picture. For now, the takeaway is simple. The closest asteroid in recorded history is coming. It is acting stranger the harder we look, and in 2029, we are going to find out what it is made of by watching our own planet squeeze it. Mark the date. The 13th of April, 2029. The whole world is going to be looking up,